Hello student, in this class we are going to discuss about elementary particles. Elementary particles are structureless particles and these are the basic building block of all the particles. Okay. According to the statistics, the elementary particles are classified into two groups, bosons and fermions. Bosons have integral spin and they obey Bose-Einstein statistics. Fermions have half integral spin and they obey Fermi-Dirac statistics. In the inverse, there is no law that control the number of bosons in the inverse, but the number of fermions is strictly conserved in the inverse. Bosons are classified into two groups, massless bosons, and the massless bosons are graviton and photon. Graviton is the exchange particle for gravitational force field and photon is the exchange particle for electromagnetic interaction. Okay, and another one, meson. Mesons mean medium mass particle and actually mesons are hadrons, they are strong interacting particles. The mesons are classified into three groups, pi meson, and in this group the particles are pi minus, pi 0 and pi plus. Another group is k meson and in this group the particles are k plus and k0 and another one is eta meson. These are the strong interacting particles and these are called hadrons. Okay. Let's see fermions. Fermions are classified into two groups, leptons, and the leptons are electron, muon and tau, and the electron neutrino, muon neutrino and tau neutrino. Tau neutrino. These are the lepton particles. Lepton means light in weight. Okay, and all the lepton particles are characterized by a quantum number called lepton quantum number. And in allowed reaction, lepton quantum number always conserved. For lepton particle, lepton quantum number is 1, and for anti-lepton, lepton quantum number is -1, and for non-leptonic particle, the lepton quantum number is 0. Actually, in every allowed reaction, the lepton quantum number is individually conserved. That means, in a allowed reaction, the electron lepton number is individually conserved, muon lepton number individually conserved, tau lepton number is individually conserved. Now let's see another class, and this is baryons. Baryons are classified into two groups, nucleons and hyperons. The mass of the nucleons is according to the mass. The baryons are classified into two groups, nucleons and baryons, and nucleons and hyperons are heavy mass particle. The mass of the hyperons is very greater than the nucleons and they are unstable particle. And the nucleons are neutron, proton and neutron, and hyperons are classified into four groups, lambda hyperon, sigma hyperon, and there are three particles, sigma minus, sigma 0 and sigma plus, and another group is xi 0 and xi minus, and another one is omega 1. Okay. Baryons are also characterized by a quantum number is called baryon quantum number, and for all the baryon particles, baryon quantum number is 1, and for antibaryon, baryon quantum number is -1, but for non-baryonic particle, the baryon quantum number is 0, and for every allowed reaction, the baryon quantum number is conserved. That means in a allowed reaction, before and after reaction, the baryon quantum number remain same. Now I will discuss these are also the strong interacting particles. Baryons and mesons are strong interacting particles and they are called hadrons. Now I will discuss about isospin quantum number, and it is very important quantum number. It has mathematical properties similar to the spin but do not have any physical relationship to the spin, and isospin quantum number is conserved in a strong interaction. If we see the pi meson particles, actually these are the three different charge states of same physical entity. Here the physical entity is one, but these are the three different charge states of the same physical entity. Okay, so if I the isospin quantum number for these three charge states, actually isospin quantum number is used to describe the different quantum state, and if I the isospin quantum number, then we can write 2i plus 1 equal to 3. Actually this is the multiplicity. Okay, so I equal to 1. If we calculate, then we can find the value I is equal to 1, and third component of isospin I3 is equal to, for pi minus is minus 1, pi 0 is 0, and pi plus is equal to plus 1. Let's see for K meson. This is also the different charge state of same physical entity, and since there are two charge states, so the multiplicity is 2, so the isospin quantum number 2i plus 1 is equal to 2 or I equal to half, and third component of isospin for K plus is equal to plus half, and for K0 minus half. Okay, and these are also the two different charge states of same physical entity, and since there are two charge states, so the multiplicity is 2 and I will be half, and for proton I3 will be plus half, and for neutron minus half. These are also the three different charge states of the same physical entity. Okay, and since there are three charge states, so the multiplicity is 3, and since for pi meson there are three charge states, so we get the isospin quantum number I is equal to 1. Similarly here the isospin quantum number will be 1, and I3 for sigma minus is equal to minus 1, sigma 0 0, and sigma plus 1, and these are also the two different charge states of same physical entity, and there are two charge states, so the isospin quantum number will be half. Isospin quantum number half for two charge states, 1 for three charge states, and if there are four charge states, then the isospin quantum number will be 3 by 2. So here I3 equal to plus half for sigma 0 and xi 0, these are the xi particle, and isospin quantum number for xi particle is plus half, and for xi 0 the I3 is equal to plus half and xi minus half. Okay, I3 is a quantum number, and this quantum number is conserved in strong interaction and electromagnetic interaction, but isospin is conserved only in strong interaction. Okay, if in an interaction isospin is conserved, that means before and after interaction, if the isospin remains same, then and if obviously the reaction is allowed, then we can surely say that the reaction is strong interaction. Okay, now another very important quantum number, it is called strangeness quantum number. Actually strangeness quantum number is used to describe the strange particle, and the particles that develop by strong interaction but decay through weak interaction are called strange particle. All the hyperons are strange particle, and K meson also are strange particles. They are developed by strong interaction but decay through weak interaction, and they are produced in pairs. We can easily calculate the strangeness quantum number if we arrange the baryon quantum according to their charge, the charge center of the baryon do not occur in a same vertical line. Actually, the strangeness quantum number S is equal to 2 into shifting of the charge center with respect to the charge center of the nucleon. If we arrange the particle, let's see, neutron having charge 0, proton having plus 1. So the charge center half at plus halfway between neutron and proton. So the charge center at half. For sigma 0, charge center at the 0. So the charge center with respect to the charge center of the nucleon, delta q equal to 0 minus half, and this is equal to minus half. Okay, so S equal to 2 into delta q, that means minus 1. So the strangeness quantum number for lambda 0 is minus 1, and for sigma particle, sigma minus, sigma 0 and sigma plus. And for sigma particle, the charge center at the 0, so the strangeness quantum number will be minus 1. Okay, and if we see xi particle having charge center at minus half. Okay, so the charge center with respect to the charge center of the nucleon, actually here we consider the charge center of the nucleon is a reference charge center, and we calculate the charge center for the different particle with respect to the nucleon. So the charge center for xi particle, delta q is equal to minus half, and this is equal to minus 1. So S equal to 2 into minus 1, this is equal to minus 2, and for omega minus, here the charge center at minus 1, so the delta q equal to minus 1 minus half, and this is equal to minus 3. And so the strangeness quantum number is equal to 2 into minus 3, and this is equal to minus 3. So we can easily calculate the strangeness quantum number for the baryon particle, but strangeness quantum number for K Meson is plus 1. Okay, and the strangeness quantum number is conserved in strong interaction and electromagnetic interaction, but for all allowed reaction, the strangeness quantum number S, delta S, must be 0 plus minus 1. This is the selection rule for the strangeness quantum number. For any allowed reaction, delta S equal to 0 plus minus 1. Now we can calculate the strangeness quantum number by using another formula, and it is called Gell-Mann-Nishijima formula, and it is Q is equal to I3 plus B plus H by 2. This is the charge, and we know charge for the elementary particle, so we easily find out the charge of the elementary particle, and I3 is the isospin quantum number, and I3 of the isospin, third component of the isospin quantum number, and for all the particles we know the value of I3, and B is the baryon quantum number, and it is 1 for baryon particle, non-baryon 0, and for anti-baryon is minus 1. So using this formula we can easily calculate the strangeness quantum number, and it is called Gell-Mann-Nishijima formula, and here Y equal to B plus S is called hypercharge, and it is also conserved in strong interaction and electromagnetic interaction. Okay, thank you.